Kia ora, welcome back. We're going to have a look at the Atmel AVR memory and the different data types that are stored within it. So we have three types of memory in the AVR. We have the flash for storing the programs. We have the static RAM, which is for storing data. And we have the EEPROM, which is for storing data also, but it's long-term, which means it'll be there when the power goes off and comes back on. We also have the registers inside the AVR, but we don't engage with those much when we're programming in C. Okay, it's only if you're going to be doing assembly that happens. Now, when you want to find out about the amount of memory that a microcontroller has, what you need to do is have a look at the data sheet. So let's go to the data sheet. Here's the data sheet for this, and you'll become very familiar with this data sheet, so you need to download it and make sure you've got it. What we've got is we've got different types here, the 48, the 88, the 168, and of course the 328, which is the one that we're using. What we're going to do is just go down this data sheet and have a look to see what the differences are between these, and here you will find that the flash memory, we have the EEPROM, and we have the static RAM. And you'll see that the different sizes of these, and these relate to these particular special versions of the microcontroller up here. So you can buy a version which has got less memory or more memory, and the reason you want to do this, of course, is to save money on a design. If you only need a small amount of memory, then don't pay for all the high amount of memory that you could get in a chip with more memory. The two chips will be exactly the same identically physically, and all the other features will be the same, but just the amount of memory. So what have we got? In our 328P, we've got 32 kilobytes, and so that's what it means, 328. So it's an 8-bit microcontroller, it's got 32K, and that means our EEPROM is 1 kilobyte, and our static RAM is 2 kilobytes. So let's just put these into this area here. So we've got 32 kilobytes there, we've got our static RAM is 2 kilobytes, and our EEPROM is 1 kilobyte. Now the differences, of course, are that this here is what we call non-volatile, which means that the power, when the power goes off, the memory is retained. Static RAM, of course, is volatile, which means that the memory is lost when the the memory is lost when the power goes off. And of course EEPROM again is non-volatile. Cool. Now we store our data into memory, and if you have a look at this funny little map of the weather of the US, I'm not sure if this is real or not, but it came from Gensel.com, and you can see that the numbers here have overflowed into ridiculous temperatures, and it's just to show off the fact that if you are using memory, you need to use the right data for the type, or the right data type for the memory that you're wanting to store. Typically we would use 1 byte for storing small numbers and multiple bytes for storing bigger numbers, and we'll go into this in detail. Down here what we've got is the list of these. Memory types in C that you may have been familiar with already are things like int, unsigned int, short, long, float, double. We don't use these names so much when discussing microcontroller programming. That's because implementations of C are allowed to change the implementation and sizing of something like an int, for instance. So on a PC you'll find that an int will be 4 bytes long, and on a microcontroller it'll only be 2 bytes long. So one of the things you want to make sure you're doing is you want to make sure that you are using these names here for variables. They're the ones you want to use. But of course then you have to understand the limitations of the data type you're using. Do not get into the habit of using things like int inside your microcontroller programs, because you might be thinking that an int is 4 bytes when it's not, it's only 2 bytes. And the difference between a 4 byte number and a 2 byte number is significant. Of course, you also, as well as the number of bytes we use, we're interested into whether it is signed or unsigned. And the difference, of course, is that the most significant bit in a signed number is used to tell you the sign. If it's a 1, then it is a negative number. If it's a 0, it's a positive number. And this uses the format called 2's complement, which you've covered already. The other thing we have to know about the microcontroller is that the float and the double are exactly the same size. We do not have 8-bit doubles in our microcontroller to use. We have 4-bit floats, and you can use float or double to refer to it. So I would suspect that using float would be the better thing to use all the time. Noting that, of course, with a 32-bit floating point number, you only get 6 decimal points of precision, and that's significantly different to something like a 64-bit number, where you will get something like perhaps 19 decimal points of precision. So you'll definitely use signed and unsigned in your programs. The difference between those, of course, is not just the fact that there is a 1 in the most significant bit for a negative number, but of course the range of numbers that you can manipulate changes significantly. The implications of getting it wrong. Well, if you get it wrong, things can happen. You want to make sure that you are using the right data type for the problem that you're working on, and there is no fixed answer to that. If you need to use a 16-bit signed or a 32-bit unsigned, then that's what you use. Typically, we want to say that you don't mix types together. If you're going to be converting from one type to another, you do a proper cast and make it explicit. Try to avoid relying on implicit casting, which follows a certain range of rules, but actually if you want to go from one type to another, then use an explicit cast. And if you want to know a little bit more about this, there's a C coding standard from bargroup.com which I'd recommend that you have a look at. Of course, when you do make errors, bad things can happen. In 1996, the Ariane rocket exploded 40 seconds after launch, $500 million cost gone. And why? A 64-bit floating point number relating to the velocity of the rocket was converted to a 16-bit signed number. It overflowed. The number was greater than 32767, conversion failed, and the rocket lost control and exploded. Yeah, be very careful about converting numbers between different types. Use explicit casts to do this. In 1991, 28 soldiers were killed and 100 more were injured. A Patriot missile was used to, well, Patriot missile systems are used to track incoming missiles to a defense point, and it failed to launch. And when they realized, when they did the investigation, they discovered that a 24-bit variable was used to store a real time in 1/10 of a second, losing some small amount of accuracy. And so there was a lack of precision. So understanding these is really important. But generally, your guidelines are use the smallest type possible and use unsigned types where possible. You want to use the smallest type possible because, well, while it reduces the precision available to you with the number, it conserves RAM, which is limited in a microcontroller. And of course, when you're manipulating larger values which are bigger than the size of the ALU, which is an 8-bit device in the AVR, it reduces your processing time if you use 8-bit types rather than 16-bit types, or you use 16-bit types instead of 32-bit types. And use unsigned types where possible, and just decomplicate your code. Take, for instance, if you were designing a car engine control unit and a number overflowed or underflowed, then your engine might just seize up completely. When you're mixing things like fuel and air together to get the right combination of combustible gases, you might find that it just explodes in the wrong time and your engine blows up, or it doesn't explode and it just stops working. So you want to make sure you're doing things correctly. From Gansel.com, there's a little survey that goes out, and here's one of the questions that's asked. If the product resulting from your current project malfunctioned, what is the worst possible outcome? And you know, often engineers don't take time to think about what it is that's going to go wrong with their product if it fails. And you're more than just an engineer, you're a designer of technology in our society, and you've got to be very careful and societal minded when you're doing this. Of course, not something you're going to run into in this course, but I've indicated that here, that you will run into this in, say, for instance, a design course or real life. These social, non-technical factors are really one of the most significant aspects of an engineer's role. If you want to know more about this, as a particularly nasty issue with variable sizes with the Therac 25, which is a device for treating cancer. And yeah, that's pretty awful reading this. What happens if underflow and overflow of variables? So I can give you a silly little example. There's a in Texas in 2003, there was this Swedish sports car, and it was being driven at 389 kilometers per hour in a 75 mile per hour speed zone. 75 miles an hour being 110 kilometers an hour, I think, maybe a bit more. And so this speed of 389 kilometers per hour. Now, if you only used an unsigned 8-bit type to store that, then what you'd find is that it can only store a number as big as 255, so it will overflow. So for instance, if we look at the number 389 in base 10, in binary, it is 110000101. And of course, what happens if it overflows is that you lose this most significant one here. It's the same as subtracting 256 from it, and you end up with 133. So that's actually, if you used an 8-bit type, then the guy perhaps might not have even got a speeding ticket, because the police officer would have thought he's only doing 133 kilometers an hour because it had overflowed. Let's have a look at when you're connecting things to your microcontroller, whether they're inputs or outputs. And this is a pretty important thing we're going to go on to next, is connecting some output devices, some LEDs to it. But in general, you need to know whether a device is an input or an output device. So thermistor, for instance, is an input device. It senses change in temperature. A liquid crystal display, an LCD, or more commonly nowadays perhaps an OLED, an organic light emitting diode, these are part of a user interface. And of course, that's an output. I've only labeled the inputs in this. A GPS receiver receives data from GPS satellites, and it allows you to track the position and the time accurately, distance, track your motion across the earth. And this is an input device. An accelerometer is an input device. It gives you 3 axes, X, Y, and Z for your acceleration. Micro switch is a little input device. It allows you to detect movement or position of something. Light dependent resistor is an input device. It measures lux or light level. Humidity sensors measure relative or absolute humidity. They're input devices. A potentiometer you could connect to an arm, and it will allow you to measure the position of something. A solenoid allows you to move things. Solenoid valve allows you to open or close a liquid valve, such as inside a washing machine. A strain gauge, you might mount one of these onto a stress member on a bridge to measure how much stress it's under. And of course, an FSR is sort of like a bigger version of a strain gauge and not anywhere as accurate. DC motor allows you to move things. It's an output device. An LED, light emitting diode, is a user interface device. 7-segment displays, very useful user interface output devices. Photodiodes are generally part of some sort of light interrupter device, where you have an LED and a photodiode together, and the photodiode acts as the input device. You have a keypad, which is an input device and part of a user interface. What I want to have a look at now is I want to look at one of the sort of general things that you need to know about. And when you're looking at Atmel Studio, which is what we're going to be using for converting your C programs into code that can be uploaded to a microcontroller, it's called a tool chain, because it's actually a fairly large chain of events which goes through. And you'll notice there's a whole bunch of files here. You start with a .c file, which is your C program. You add to it header files that you may have created, or you're pulling in with other file from a library. This develops a .i file, which is cross-compiled into a .s file. Then it becomes, after it's been assembled, into a .o file. It's linked then with the library files that you've pulled in via your header files, and this becomes a .elf file, which can go to the internal debugger on the ML Studio. And it can also just be used then to create the .hex file, which is actually the assembled assembly code which goes into your micro. Another output here is the .lss file, which is something that we've already had a little bit of a previous look at, and it's quite an important one. It allows you to investigate exactly what's going on. In terms of this control of this whole process, this is covered by a make file. And the make file is a very important part of it. You don't normally interface with this in this course, but knowing that a make file controls all of this process is very important, especially when it comes to optimization settings. How well your code is optimized. If you look at the optimization settings in ML Studio for your particular program that's open, you normally want to be using optimization level 1 and just stick with that for this at this stage. Later we'll learn a lot about a keyword called volatile when we're declaring variables, and that's really important because it helps avoid issues with optimization that you can get into. So that's just a little bit of an overview of the IDE, the Integrated Development Environment in ML Studio. We're going to have a look now at the interrelatedness of hardware and software, and I want to look at, this is the first of our programs in the assignment. So I'm just going to flash the assignment up here. So here's this program, it's actually question 12, which is the first of these simulation programs. And what happens here is that you can run this code and you can see that the LEDs work in a nice little flashing pattern like this. Now, what I want to do is I just briefly stop this, and I want to look over my shoulder here at my Cylon, which is going. And I'm just going to zoom in on the Cylon there. Now this Cylon device here that I've developed has got or the Cylon helmet. It's a little cardboard one which is it's been knocked around a bit over time, but it's got 32 LEDs and it's actually been driven 5 at a time. Now I'd like to start you with 32 LEDs, but that's actually a bit complex. I want to start you then in different in a different scenario. For instance, I might start you with a baby Cylon device which only has 8 LEDs. So we're going to look at, you know, a little 8 LED Cylon device program. So let's go back to our little 8 LED Cylon device, and I'll run this now, and you can have a look at this program, and I'll just run through how it's working. If you look at this pattern as it's going, you can see the 3 LED pattern. Oops, there's a little glitch in it, and this is the glitch in this is what you have to fix in your program. And what I'm going to do now is I'm just going to stop this, and we're going to look at this line by line to see what's happening. Let's step the program through one step at a time. This is the first line of code. Let's just make this a bit bigger, make it a bit clearer. There we go. So what we've got in this first line of code is DDRD0XFF. So what this does is it tells this port of the microcontroller that we're going to be making all of these pins outputs. A device can't be both an input and an output at the same instant. These pins, they have to be inputs or outputs. And so we have a register that controls the direction of this, and it's the DDRD, so Data Direction Register for port D. Now if we step down into our program, what we're going to do is we're going to say we're going to turn on one of these LEDs, and you can see that the port is labeled 76543210, so the least significant bit in port D, we're making a 1, which turns on the LED. And then what we do, the next thing we do is we step into this, and we have a delay of 100 milliseconds. And the next line of code is to turn on the 2 LEDs. So as we step through this, you can see that we're going to be turning on the subsequent LEDs. The next step, of course, is to turn on just these 3 LEDs, LED 3, 2, and 1, which means turning off LED 0. And you can see that this is what's going to happen in this line of code. We're going to turn off this LED, and we're going to turn on this LED. So we just step here like this. And as we step through, you can see the pattern shifting because of the different combination of ones and zeros in the port register. And we'll look in detail at the particular registers. So remember, at this stage, I've introduced you to two registers. The data direction register tells you which way around these pins are. Are they inputs or outputs? In fact, by default, they're configured as inputs. And if we want them to be outputs, we have to write a 1 into the data direction register. So I'm writing in 1s into all of these. I can have a look at my registers over here and see what's actually happening in my registers. So I'll just stop my program. And as I step through my program, the first thing that's going to happen is I'm going to write 1s into DDRD. So DDRD is this register here. So as I just step into this, you'll see that's what's happened. These pins are all set to 1, which means they're all going to be output. And port D is this register, and as we go through the program, you can see that it's changing. Putting a 1 in here is making this output high, which is turning on this LED. And as we go through this program, you can see that it's going to just change the position of the pattern by actually turning on and off sequences of LEDs. Now, as I step through this program, you're going to see that there's an error at one point. So this is correct. It goes to one LED, then they go off. One LED comes back on, 2, 3, and if I'm scrolling down, you can see the pattern is actually fairly obvious in these 1s and 0s. 1 here, 2 here, 3 here, 3 here, 3 here. So as we step through, you'll see that we're going to get a point where there's an error. And so here's the next step in the pattern, and then there's an error in this pattern here at this point. So this is where you've got to stop the program. You've got to remember, now which point was it? It's this one here, it's line 84. So remember which line it was. And then you can fix that and submit the answer to your problem. So this is just looking through to see how this program works and getting you used to the idea that these register values control the outputs. So this is the relationship between hardware and software, which is one of our key learning outcomes in the course, is to understand this relationship of how hardware and software interrelate. So just to review that, what we've got is we've got DDRD equals 0xf. So this is data direction register for port D. We're going to make them all high, which means they're all going to be outputs. And then the port register itself is going to be driven with different values, different sequences of 1s and 0s to turn on LEDs. Now, if you don't have the delay milliseconds in here, and you won't see this in the simulator because the simulator is running, and it's a JavaScript simulator running inside a browser, so you can't run it at full speed of a microcontroller. But if you didn't have these delays, these LEDs would just appear to be on dimly because they're running so fast. Now, in normal C code, and this is the final little bit for this part of the lecture, you will find that you don't have a while loop like this. This is the unique aspect of a microcontroller, and this is how you turn it into what's called an automaton. Now, an automaton means something that is powered up and runs unattended by people until it is powered down again. And that's really what an automaton is. It's just a machine that is completely automatic. And the way that happens is that inside your normal void main program here, there's a while loop, and this while loop has a while 1. And while 1 means do whatever is in the braces while whatever is in the brackets is true. And of course 1 in C is always true. That's how we define true. 0 is false, 1 is true, or anything other than 0 is actually true. So I could have put 100 in there, but while 1 is typically what you will see. And of course that means that the code will always be trapped within this while loop. It will never be able to exit it because 1 is always true, and so it will never get to the end of your main. Okay, so I'm just going to pause this and quit this lecture here now. So that's the end of the first lecture, and I want you to go away now and do some of those questions in the assignment. Cheers.